Consider the region R defined by x is greater than or equal to 0, x plus 2y is greater than or equal to 8, x plus y is less than or equal to 6. We need to graph the region on graph paper. We need to find how many points in region R have integer coordinates, how many of these points obey the rule y minus x equals 4, and we need to find the greatest and least values of 2x plus y for all x, y that are elements of the region with integer coordinates. I think B, C and D will become a lot easier once we actually have a look at the region. So we need to graph these three separate lines really. If we are interested in x is greater than or equal to 0, we need to really draw the line x equals 0, x equals 0. Also, because it's greater than or equal to, that means it's a solid line. Anything greater than or equal to, less than or equal to, solid line. If it's greater than or less than, that's your dashed line. So if you look at these, all of these are going to need a solid line, so that's quite handy. Right, what should we draw? Okay, so x equals 0 is a quite easy line. It's just the y-axis already kind of drawn really, but I'll draw it anyway. So that's this line, and then remember we need to shade unwanted regions. So we need to kind of think the opposite. If the region we're interested in is x is greater than or equal to 0, so the region we don't want is the opposite. It's when x is less than or equal to 0, or just less than 0 in fact. So what that means, we're going to sort of shade this bit out. This is the unwanted area. I'll try and leave the numbers so you can still see them. So this is the first line, which is x equals 0 drawn. Can I just write that in? So that was x equals 0. Okay, so the next line is a little bit more complicated. X plus 2y is greater than or equal to 8, so we need to consider x plus 2y equals 8. And yes, you could, because it's quite a simple one, you could potentially put it in y equals mx plus c form, but I still think it's easier just to think about these axes intercepts. So you think if x equals 0, we're going to have 0 plus 2y equals 8. 2y equals 8, so y equals 4. So that means that 0, 4 is a point. So what we can do, go to our graph. I'll do this one in a different colour. We can go to our graph and we can just plot this point 0, 4. So 0 along and 4 up, like that. And then we can do exactly the same for if y is 0. If y equals 0, well, you would have x plus 2 times 0 equals 8. So that would be x equals 8, which means that it goes through 8 and 0 as well. And if we go back to our graph, 8 along, 0 up, that is another point on the line. Remember, we're drawing this with a solid line because it's a greater than or equal to inequality. So let's just pick a colour. Right, so we just need to draw the line that goes through these points. Just like that. You can extend it. I can potentially extend the other way as well, but I haven't got a lot of graph, something like that. And remember, we want to shade the unwanted region. So the region that we want is when x plus 2y is greater than or equal to 8. So that's, you want stuff that's above the line, greater than. So we're going to shade the unwanted region. That's when it's less than. So that must be the other side, underneath. When you talk about less than, in the context of regions, it means kind of to the left of a line or underneath the line, so at the bottom of it. Something like that. This is actually how I would recommend. It's a bit tedious with a computer, but I would recommend shading your unwanted regions in this kind of hatching style. Just drawing lines, I really don't want you to spend time actually shading and shading, make it some kind of artwork. You don't have time for that. It doesn't help you in any way. Right, so I should make a point of what that line was. That was x plus 2y equals 8. X plus 2y equals 8. Okay, so for x plus y is less than or equal to 6, we need to draw x plus y equals 6. And you're just looking for pairs of values that add up to make 6. So if x was 0, y would be 6. If y was 0, x would be 6. And I mean, you could even, because it's so simple, you can say 3 and 3 as well. 2 and 4, 1 and 5, and so on. But 0, 6 and 6, 0 are probably the best two. Firstly, because it's probably the easiest. Secondly, because it will cover, looking at the axes, it will cover the whole thing. So we need 0, 6 and 6, 0. So that would be here. 6, 0. And 0, 6 is up there. Okay, and we just need to join with a line. Can extend. Just like that, and again we want to shade the unwanted region. So the inequality in question is x plus y less than or equal to 6. So we shade the exact opposite way, it's greater than or equal to. So we're going to shade the other side. So this region here. We're going to shade like that. I'm going to have to draw quite a few lines, so I'll probably spread them out a bit. But you can see now we've got this region emerging, quite a small region actually, and that is the accepted, the wanted region. Some say if you ever do linear programming, they call it the feasible region. Technically that's off the scope of the course, but I have seen some linear programming in one of the paper 6s, which we'll cover later on. So now we are left with this unshaded region, and that is our region R. So that is the region. Just going to stay away from points for reasons that will become clear in a minute. So we've graphed the region R on grid paper. There it is. Right, how many points in R have integer coordinates? It says integer just means whole numbers. So if we just go into R, and I need to find everything in here where it has integer coordinates. So basically, when is it actually on the diagonal of a square? And remember, the lines are part of the region because of the nature of the inequalities. So I'm going to try and draw these. Hopefully yours will look a lot neater. I'm just going to try and make all these marks. That is okay. So it's not completely clear. I think it's just because of my lines. I think that point probably is fine. And here. And that looks like all of the integer points. So that there are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points in R have integer coordinates. So part B, the answer is 9. Part C, how many of these points obey the rule y minus x equals 4? Now there's other ways you could sort of get every point and sort of just check, but it's probably easier just to sort of draw y minus x equals 4. So if we had y minus x equals 4, if we could, well, if y was 0, 0 minus 4 equals 4, so that might not be so easy. So what about, say, 5 minus 1 is 4, isn't it? So that could mean that it could go through if y was 5 and x was 1. What about 6? Should we go a bit bigger? So if y, we can go up to 8. 8 minus 4 is 4, so it could be 4 and 8 as well. So there are 2 points on the graph of y minus x equals 4. And if we just kind of draw that, we can see which ones of these orange points are actually on there. So if I go ahead and plot the points 1, 5, so 1 along and 5 up, is actually definitely a point in the region. 1, 5 and 4, 8. 4 along, 8 up is up here. So then if I just draw the line through there, and it looks like I've passed through an orange point. I'll just go over my orange points again. I've passed through a point there and a point here. So it looks like two of those integer points in the region obey the rule y minus x equals 4 because they are on the line y minus x equals 4. You could potentially check. So here y is 5 and x is 1, so y minus x is 4. And here y is 4 and x is 0, so 4 minus 0 is also 4. So the answer to part D, it was 2 points. Okay, for part D, find the greatest and least values of 2x plus y for all of x, y that have in the region that have integer coordinates. Now again, this is kind of linear programming without calling it linear programming. There would be some kind of cost function, some kind of maximizing or minimizing some kind of industrial process. You don't need to know that, but what you do need to know, if we don't need to test all of these points, we're going to find greatest and least values of this thing. We only need to worry about points on the edge of the region, so on the boundary, and those points are going to be here at the top here at 0, 6. In fact, let me just do that in a different colour. That's a point we definitely need to look at on the boundary. Here we've got this other point on the boundary at 0, 4. Then we've got a point at 4, 2, and actually they are the only points. So all of these other values, they're not going to return greater or less or smaller results than the things on the boundary. Now I've got a triangular region. It may be that you end up with a region with more corners and more vertices, in which case yes, you'd need to try more. In this case I only need to consider the 3 points. So the 3 points are 0, 6 and 0, 4 and 4, 0. So that's the point. It's the integer point in the region. Remember, they are on the boundary. If I tried all the points in the region, they will be sort of in between these extreme values. One of these is going to give the least value, and the other one's going to give the maximum. And then I just want to, at these points, I want to see, well, what's the value of 2x plus y? So if x is 0 and y is 6, well, 2 times 0 plus 6, that is 6. If x is 0 and y is 4, it's 2 times 0 plus 4, which is 4. And if x is 4 and y is 0, you're going to have 2 times 4 is 8 plus 0, which is 8. So the greatest and least value, the greatest value equals 6. So maybe this is number D. Greatest value equals, greatest value equals 8, least value equals 4. And if you want to, if you don't believe me, you can go off and test all of those orange points and see if you can get a smaller or a greater value for 2x plus y. But I'm telling you, you will not. And if you see a question, well, I'm going to give you a follow-up question. That is the approach you should take. It will save you some time. Just use the points on the extreme boundary, unless, of course, those points aren't in the region. For example, if these inequalities had not been greater than or equal to, if they had been greater than, that might be a bit different then.